Preparing for a systems engineering at Fastly interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a globally distributed content delivery network? I would place edge points of presence close to users, route requests using DNS or anycast, and terminate HTTP connections at the edge. Each node would cache immutable and safely cacheable content, while shield regions protect origins from request floods. I would add health checks, automated failover, capacity headroom, and observability for latency, errors, and hit ratio. Fast purging and clear cache control semantics are essential. The design trades stronger origin consistency for lower latency and resilience. While answering, cover edge locations, DNS or anycast routing, cache hierarchies, origin shielding, health checks, consistency, latency, capacity planning, and how you would measure cache hit ratio and customer perceived performance. Question 2. Explain how HTTP caching works and how you would troubleshoot a low cache hit ratio. HTTP caching stores a response against a cache key, usually derived from the URL, method, host, and selected headers. I would inspect cache control, vary, cookies, query parameters, and authorization behavior first. Then I would compare hit, miss, pass, and error rates by path and geography. Common fixes include normalizing irrelevant query strings, removing accidental cache busters, setting appropriate TTLs, and using conditional revalidation. I would never cache personalized responses without explicit safety guarantees. Make sure to cover cache control, etag, last modified, vary, TTLs, cache keys, cookies, query strings, bypass rules, revalidation, stale content, and metrics that distinguish misses from origin failures. Question 3. What is cache purging, and how would you build a reliable purge system? Cache purging invalidates stored objects before their normal expiration. I would support exact URL, surrogate key, and service-wide purges, with authenticated requests and strict rate limits. A durable queue would fan changes to every edge, using idempotent messages, retries, acknowledgements, and dead letter handling. I would expose propagation status and measure time to invalidation across locations. The key trade-off is breadth versus cost. Global purges are simple operationally but can create origin load immediately afterward. In your answer, talk about purge by key, purge by tag, propagation latency, idempotency, retries, authorization, auditability, rate limits, failure handling, and how you would verify that stale objects are no longer served. Question 4. How would you investigate an increase in latency for requests passing through Fastly's edge? I would first define the affected population by region, host name, protocol, status, and cache state. Traces should separate DNS, TCP, TLS, edge processing, queuing, origin connection, and origin response time. I would compare current data with a known good baseline and check deployments, capacity, packet loss, and provider dependencies. A cache miss with slow origin time suggests a different owner than slow edge processing. I would mitigate safely, communicate scope, then confirm recovery with user-facing percentiles. Be sure to mention request tracing, edge versus origin timing, DNS, TLS, TCP, queuing, cache status, geography, saturation, recent deployments, dashboards, logs, and controlled comparisons before changing production configuration. Question 5. What are the advantages and risks of running application logic at the edge? Edge execution moves decisions closer to users, reducing round trips for routing, authentication checks, redirects, personalization, and request transformation. It also lowers origin traffic and can continue serving useful behavior during origin degradation. The risks are limited CPU and memory, distributed debugging, fragmented state, deployment blast radius, and consistency across locations. I would keep edge functions deterministic and stateless where possible, externalize durable state, define strict budgets, and test globally before gradual rollout. Focus on latency reduction, reduced origin traffic, isolation, execution limits, state management, deployment safety, security, debugging, consistency, and when edge logic should remain lightweight instead of becoming a distributed application platform. Question 6. How would you design rate limiting for a high-volume edge service? I would begin by defining the protected resource and identity, API key, account, IP, root, or a combination. A token bucket handles sustained rates while allowing controlled bursts. Exact global counters are expensive, so I would choose regional enforcement, replicated state, or approximate sketches depending on risk. Limits should return 429 with useful retry information and be observable by tenant. For security-sensitive endpoints, I favor fail-closed behavior. For availability-critical content, bounded fail-open behavior may be safer. Discuss token buckets or leaky buckets, identity selection, distributed counters, approximate enforcement, burst handling, fairness, fail-open versus fail-closed behavior, response codes, and protecting both customers and origins. Question 7. Describe a secure design for TLS termination at the edge. At the edge, I would automate certificate issuance, validation, renewal, and deployment, storing private keys in tightly controlled systems with audit logs. I would support SNI, modern TLS versions, secure cipher suites, and optional mutual TLS for sensitive clients. Connections from edge to origin should also use authenticated TLS rather than relying only on the client-facing hop. Rotation must be overlapping and atomic, with monitoring for handshake errors, expiration risk, and regional deployment failures. Cover certificate provisioning, renewal, private key protection, TLS versions, cipher policy, SNI, mutual TLS, origin encryption, session reuse, observability, compliance, and safe certificate rotation without interrupting customer traffic. Question 8. How do DNS and anycast affect a globally distributed edge platform? DNS routing directs clients toward an address based on resolver behavior, geography, health, or policy, but cached answers make failover slow and imperfect. Anycast advertises the same IP from multiple locations, letting network routing select a nearby path and shifting traffic quickly when advertisements change. Anycast simplifies client configuration but can create path instability and uneven regional load. I would combine both thoughtfully, monitor BGP and traffic distribution, and avoid assuming geographic proximity guarantees network proximity. In your answer, explain recursive caching, TTLs, health-based routing, BGP anycast, route convergence, traffic engineering, failure domains, regional imbalance, and why DNS and anycast provide different operational trade-offs. Question 9. How would you troubleshoot intermittent 5xx errors at the edge? I would segment failures by status code, POP, customer, URL, protocol, cache state, and time window. Request IDs should connect edge logs, origin logs, and traces. I would distinguish origin-generated errors from edge timeouts, resets, TLS failures, and policy responses. Then I would correlate the rise with deployments, saturation, dependency health, and network changes. I would avoid blind retries because they can worsen overload while using bounded, idempotency-aware retries where recovery is demonstrably safe. Make sure to cover status code classification, request IDs, origin health, timeouts, connection resets, retries, cache behavior, geography, deploy correlation, logs, traces, packet data, and minimizing retries that amplify overload. Question 10. What Linux concepts are most important when operating high-throughput edge servers? I pay particular attention to run queues, CPU saturation, memory reclaim, file descriptor limits, socket states, listen and accept queues, retransmissions, and network device drops. Tools such as PIDstat, SS, VMSTAT, IOStat, perf, and eBPF help connect symptoms to causes. I also consider NUMA locality, interrupt distribution, and connection churn. Before tuning, I establish a baseline and reproduce safely. Kernel changes should be measured incrementally because improving one bottleneck can expose another. Discuss CPU scheduling, memory pressure, file descriptors, socket states, TCP queues, interrupt handling, disk and network I/O, NUMA, process limits, kernel metrics, and safe capacity diagnosis under production load. Question 11. How would you choose between a process, thread, and event-driven architecture for an edge service? I choose based on the workload and failure boundary. Processes provide strong isolation but consume more memory and require explicit communication. Threads share memory efficiently, though races and one faulty thread can affect the process. Event-driven designs handle many mostly I/O-bound connections efficiently, but blocking work must be eliminated or offloaded. For an edge proxy, I typically favor event-driven networking with isolated workers, bounded queues, and clear backpressure. CPU-heavy transformations may need separate worker pools. Focus on isolation, scheduling overhead, shared state, blocking operations, concurrency, fault containment, debugging, language runtime behavior, and workload characteristics such as connection count, CPU intensity, and latency sensitivity. Question 12. How would you design observability for a distributed edge service? I would define user-facing SLOs first, such as availability, latency percentiles, and successful request rate. Metrics provide fleet-wide trends, structured logs capture detailed decisions, traces show where time is spent across edge and origin. Every request should carry a correlation identifier, while high cardinality data is controlled through sampling and targeted dimensions. Alerts should detect meaningful budget burn rather than noisy thresholds. I would also redact sensitive data and preserve enough context for incident reconstruction. Be sure to mention metrics, structured logs, distributed traces, high cardinality dimensions, percentiles, exemplars, correlation IDs, SLOs, sampling, privacy, alert quality, and dashboards that support rapid diagnosis. Question 13. What makes a distributed system resilient to partial failure? Partial failure means some components work while others are slow, unreachable, or returning incorrect results. I use deadlines, bounded retries with jitter, circuit breakers, bulkheads, and backpressure to prevent local problems from becoming outages. Operations should be idempotent, and degraded behavior should be intentional, such as serving stale content or omitting optional features. Health checks must test meaningful dependencies, not merely process liveness. Redundancy helps only when failure domains are genuinely independent. In your answer, cover timeouts, bounded retries, circuit breakers, bulkheads, graceful degradation, health checks, quorum choices, idempotency, backpressure, redundancy, and explicitly modeling dependencies that fail independently. Question 14. How would you safely roll out a configuration change across thousands of edge nodes? I would treat configuration as versioned, validated code. The pipeline should test syntax, policy behavior, resource limits, and representative traffic before deployment. I would release to a small canary set, then expand by independent regions or customer cohorts while watching error rate, latency, saturation, and cache behavior. Each version needs an atomic activation point and fast rollback. Offline nodes should converge safely later, and every change requires ownership, auditability, and an explicit success criterion. Discuss validation, versioning, staged deployment, canaries, regional waves, automated rollback, configuration consistency, blast radius limits, observability, audit trails, and handling nodes that are offline or lagging. Question 15. How would you handle a sudden traffic spike or flash crowd for a popular object? For a popular cacheable object, I would collapse concurrent misses so one request fetches from origin while others wait or receive stale content. Shielding reduces duplicate origin fetches across edge locations, and stale while revalidate preserves availability during refresh. I would monitor origin connection counts, queue depth, and regional capacity, applying admission control if needed. At the same time, I would inspect traffic signatures for abuse. Pre-warming can help predictable launches, but uncontrolled warming can itself overload origins. Cover request coalescing, cache warming, stale while revalidate, shielding, admission control, origin protection, capacity headroom, abuse detection, and distinguishing legitimate demand from an attack. Question 16. Explain how you would prevent cache poisoning and cache key vulnerabilities. Cache poisoning occurs when an attacker influences a response that later serves to other users. I would define the cache key explicitly, validate hosts, normalize query parameters, and ensure every response affecting header is keyed or safely ignored. Personalized or authenticated responses should bypass shared caching unless their variation is provably represented. I would also defend request parsing against smuggling and reject ambiguous inputs. Security tests should attempt header, parameter, and host manipulation while verifying cache behavior. Make sure to cover unkeyed headers, host validation, query normalization, vary behavior, request smuggling, response headers, authorization, input validation, poisoning tests, and separating public from personalized content. Question 17. How would you design origin failover for a customer-facing service? I would first establish whether the application supports active-active writes or requires a primary origin. Routing can select healthy origins using edge health checks, but health must include meaningful application behavior and dependency readiness. Requests should fail over only when methods are safe or idempotency keys exist. I would drain unhealthy connections, add hysteresis to prevent flapping, and document failback procedures. Replicated data, session handling, and observability determine whether failover improves availability or merely moves failures. Discuss active-active versus active-passive origins, health checks, DNS or edge routing, connection draining, retry safety, data consistency, failback, state replication, and preventing oscillation during transient failures. Question 18. Tell me about your approach to incident response during a large production outage. I start by confirming impact, assigning an incident commander, and creating a shared timeline. One group mitigates, often through rollback, traffic shifting, disabling a feature, or serving stale content, while another investigates. I provide concise updates with scope, current hypothesis, customer effect, and next checkpoint. Decisions should favor reversible actions and measurable recovery. Afterward, I lead a blameless review that identifies system and process contributors, assigns owners, and verifies corrective actions through testing. Focus on detection, severity assessment, incident command, communication, mitigation before diagnosis, clear roles, rollback decisions, customer updates, timelines, evidence preservation, and blameless follow-up actions. Question 19. How would you build a capacity planning model for edge infrastructure? I would model demand using requests per second, bandwidth, concurrent connections, object size, cache ratio, CPU cost, and geographic distribution. Average traffic is insufficient. I include seasonal peaks, flash crowds, and the loss of a major location or service pool. Load tests should represent realistic cache misses and protocol mixes. Capacity targets include safety headroom and recovery capacity, not merely normal operation. Finally, I compare hardware, bandwidth, and operational costs against latency and availability objectives. In your answer, cover traffic forecasts, workload profiles, peak-to-average ratios, CPU, memory, bandwidth, connection counts, failure headroom, regional constraints, load testing, and cost-performance trade-offs. Question 20. How would you improve a systems process when the requirements are ambiguous and multiple teams own dependencies? I would turn ambiguity into explicit assumptions, user impact statements, interfaces, owners, and measurable acceptance criteria. I would map dependencies and failure modes, then validate the highest risk assumptions with small experiments or production-safe tests. For cross-team work, I prefer written design notes, decision logs, and clear escalation paths. I would sequence delivery around reversible milestones and operational readiness, including dashboards and rollback. Strong systems engineering combines technical depth with disciplined coordination and ownership. Be sure to mention clarifying user impact, defining interfaces, identifying owners, documenting assumptions, creating measurable success criteria, sequencing risks, communicating trade-offs, and validating the design with operational stakeholders. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.